Welcome back to the deep dive. Today, we're going to be looking at model inversion attacks and defenses. I think you'll find this one pretty interesting. We're working with excerpts from a paper called MIBench, a comprehensive benchmark for model inversion attack and defense. And this deep dive is going to be a little different. I mean, since you're already an expert in machine learning, we can skip the ELI 5 and kind of like go straight into the technical nuances of the paper. Our goal here is to dissect the key findings and give you a really solid overview of this critical area of AI security. Joining me today is an expert who shares our passion for all this complex machine learning stuff. So let's just jump right in. What exactly is a model inversion attack?
So a model inversion attack, or MI attack for short, is basically this adversarial technique. The goal is to reconstruct the training data, the sensitive stuff that was used to make a machine learning model. It's kind of like reverse engineering the model to expose the data it was supposed to be protecting.
Okay, so that sounds pretty unsettling, to be honest.
Okay.
The paper mentions equation 1 as like a mathematical way to represent this whole attack process. Can you break that down for us a bit?
Yeah, definitely. So equation 1 basically turns the MI attack into this optimization problem, right? You've got a trained model, you know its outputs. The attacker, they're trying to find the input values that would create those exact outputs. It's like solving for x in the equation fx, y f is the model, y is the output we know, and x, that's the sensitive training data we're trying to get back.
I see. Okay. The paper gives this pretty chilling example of reconstructing facial images from a facial recognition model. That's some serious privacy implications right there.
Absolutely, yeah. And it's important to remember that MI attacks, they're not all the same. You've got white box attacks where the attacker knows everything about the model, like the architecture, the parameters, the whole shebang. Then you've got black box attacks where they only have access to the model's inputs and outputs. Think of it like this: white box is like having the blueprint of a house. Black box is like trying to figure out the layout just by watching people go in and out.
Okay, got it. Table 1 in the research lists a bunch of different MI attack methods. It's
Yeah.
interesting to see all the different ways attackers can try this. What are some of the things that stand out to you from their analysis of these methods?
Well, they looked at a ton of different MI attack methods, both white box and black box, using a bunch of metrics. Accuracy, feature distance, and FID score are really the big ones. Accuracy is like how close the reconstructed data is to the original training data. Feature distance looks at how similar the features from the reconstructed data are to the original features. And FID score, that's all about how realistic the reconstructed images look, especially for image attacks. So what they found was that methods like PLGMI and LOKT, they were awesome at accuracy and feature distance, meaning they're really good at recreating data that's super close to the original training set, even if it's not visually perfect. Then you've got methods like PPA and C2FMI, which use these fancy generative adversarial networks, or GANs. They scored really high in FID, meaning they can make really realistic looking images, even if they're not always perfect copies of the original data.
So there's this trade-off between how accurate and how realistic the reconstruction is, depending on how they attack. But thankfully, the research doesn't just stop at attacks, right? They also look at how to defend against them.
Right. Exactly. They explore two main types of defenses. First, there's model output processing. This is all about messing with the model's output to make it less useful to attackers. Think like adding noise, blurring the image, or rounding off numbers, anything to make it harder to reverse engineer the original data. And then there's robust model training. This focuses on building models that are naturally resistant to MI attacks. Things like differential privacy, where you add noise during training, or adversarial training, where you train the model specifically to resist these attacks. Table 2 in the paper breaks all this down with details about each defense strategy, how they work, and how effective they are.
I saw that they actually created a tool called MIBench. It seems like a pretty useful resource for checking out these attacks and defenses. What is that all about?
Yeah, so MIBench is like this platform for testing out MI attacks and defenses. It's built with a modular structure, which you can see in Figure 1. There are these 4 main modules: data preprocessing, attack, defense, and evaluation. So researchers can mix and match data sets, attack methods, and defense strategies. It's a really flexible way to run experiments and see what works best. This modularity lets them do really thorough testing and figure out the strengths and weaknesses of all these different approaches.
So it's like a virtual lab for MI research, basically. The paper mentions they used 4 data sets: FFHQ, MetFaces, FaceScrub, and Celeba. Why those specific data sets?
They picked those data sets strategically because they're all relevant to facial recognition, and facial recognition is a prime target for these MI attacks. FFHQ and met faces are big, high-quality data sets that people usually use to train generative models, like GANs. Those are super important for a lot of MI attack methods. Then you've got face scrub and SLABA. People use those all the time to test MI attacks, especially against facial recognition models. They're a good balance between how hard the attack is and how relevant it is to real-world stuff. They also split up and pre-process these data sets, making sure the resolution and image quality were consistent across all the experiments. That way they can make fair comparisons.
Makes sense. I mean, facial recognition is everywhere these days, and those models are often trained on really sensitive data, making them a pretty tempting target for MI attacks. So let's get to the fun part. What were some of the key findings from their experiments?
Well, they set up the experiments to give a thorough evaluation of different MI attack methods under different conditions. Table 3 shows how well each attack method did on those data sets, like we talked about. Some methods were killer at accuracy and feature distance, while others, the ones that used Jan priors, were better at FID. It shows you have to choose between those things. They also looked at how resolution affects attack effectiveness. They found that methods with strong Jan priors, like Mirror, C2FMI, and PPA, kept low FID scores even at higher resolutions. So they're much better at making realistic-looking high-res images compared to the methods that use simpler priors.
Interesting. So the attack method and using those Jan priors are really important for a successful MI attack. But what about the model itself? Does the model's accuracy make it more or less vulnerable to these attacks?
That's a great question. Figure 4 shows a pretty clear link between how well a model predicts things and how successful MI attacks are against it. Basically, the more accurate a model is, the easier it is to attack and get that training data back. That's because a more accurate model tends to leak more information about the data it was trained on just through its predictions. But it's not always a simple relationship. Different attack methods are affected differently by how good the model is at predictions. Early methods like GMI and KE-DMI are kind of all over the place. But newer methods like PLGMI and PPA, they get consistently better at attacking as the model gets more accurate. It really depends on the method, the model, and even the dataset itself. It's complicated.
Speaking of data sets, the paper goes deeper into that in Appendix C.3, talking about how the choice of data set affects attack success. They specifically compare using met faces as a prior versus using FFHQ. What did they find there?
Well, they saw that attacks that used met faces as a prior had a tougher time compared to the ones using FFHQ. It seems like this difference is probably because of a distribution shift between met faces and the real data used to train those target models. Met faces is a great data set, high quality and all, but it has some quirks that make it less effective as a prior when you're going after models trained on more diverse real-world data.
That makes sense. If the attacker's prior knowledge, the data set they use, isn't a good match for the real data, the attack is going to struggle. Figures 6 and 7 really show this visually. You can see the artifacts and inconsistencies in the reconstructions from attacks using met faces compared to the more realistic results they got using FFHQ. It highlights how important that dataset choice is, not just for training accurate models, but also for understanding how well different attack strategies are going to work.
Exactly. That choice of dataset can really change how realistic and accurate the reconstructed data is, and that directly affects how well the MI attack works.
Beyond just the dataset, the paper also digs into the specifics of the attack process, like the loss function used during optimization. Appendix C.6 has some interesting stuff about this. What did they find about how different loss functions affect the PPA attack method?
They found that the choice of loss function can make a big difference in how well that PPA attack works. Specifically, they found that the Poincare loss function gave them the best results without any model augmentation, while the logit loss function worked best when they did use augmentation. So it seems like there's no one-size-fits-all loss function. It really depends on the specific attack method and whether you're using augmentation techniques or not.
So there's a bit of fine-tuning involved depending on what the attacker is going for. The paper mentions these computationally intensive attack methods, RLBMI and VMI, in Appendix C.7. Because they're so computationally heavy, they had to run their experiments on a smaller scale using a subset of the SLABA dataset. What did they learn from those experiments, as shown in Table 22?
Even though the experiments were limited, the findings about RLBMI and VMI are still really insightful. RLBMI, which uses reinforcement learning, is a black box attack method. It showed a lot of promise, getting pretty good results for accuracy, feature distance, and FID. This tells us that even when the attacker doesn't know much about the target model, those reinforcement learning attacks can be a real threat. VMI, on the other hand, didn't perform as well as other methods, even though it's solid in theory. It could be because the optimization process is pretty complex. You have to keep updating the parameters of a flow model, which might make it less efficient overall.
It's interesting how these attack methods perform so differently. It shows how much MI attacks are evolving and how new techniques keep popping up. It's like a constant back and forth between attackers and defenders. Table 23 in the paper looks at how the PPA attack method works with different numbers of latent vectors and iterations. What were the main takeaways from that?
They found a pretty interesting pattern. As they increased the number of latent vectors in the PPA attack, the performance generally got better. But then it sort of plateaued after a certain point. Adding even more vectors didn't make much difference. The same thing happened with iterations. More iterations meant better results, but the gains got smaller and smaller. This shows there's a balance to strike between how much computational effort you put in and how much better the attack gets. Attackers have to think strategically about this to get the most out of their attacks without running into computational limits.
It's all about finding that sweet spot between effort and results, I guess.
Shifting gears back to the defenders, Appendix C.5 looks at how well defenses work on models with lower accuracy. What did the research reveal about that? Their findings suggest that defenses are actually more effective when you use them on models that aren't as accurate. This implies that making a model less accurate on purpose could be a way to protect it from MI attacks. It's like a trade-off. You sacrifice some accuracy to make the model more secure. This highlights how important it is to think about privacy right from the start when you're designing a model, not just focusing on getting the highest accuracy possible.
That ties back to what we were discussing earlier about balancing model performance with privacy. It seems like finding that balance is key, according to the paper. Speaking of which, the paper doesn't explicitly go into detail about how defenses perform on models with reduced accuracy. Did they mention anything about that at all?
They did, actually. They looked into this in some depth and found that a lot of the common defense mechanisms don't work as well when you apply them to really accurate models. This suggests that our current defense strategies aren't really up to the task when you need a model to be super accurate. It underscores a need for new defense strategies that can protect privacy without sacrificing much accuracy, especially in applications where accuracy is absolutely critical.
That's a crucial point. We can't just keep building more and more accurate models without thinking about how to make them privacy preserving as well. This research really shows how much more work needs to be done in this area.
Yeah, it really feels like we're at this turning point in machine learning. We have to start putting privacy on the same level as accuracy. This research really makes that clear. Exploring these attack and defense methods and building tools like MIBench, it's giving researchers and developers really valuable information about how to make AI more secure. Before we wrap up, are there any findings from this paper that really stand out to you, or any areas you think we need to explore further? Well, the paper shows us a big challenge we face as models get more and more advanced and accurate. It's that tension between how useful a model is, which we usually measure by accuracy, and how well it protects privacy. It's a tough balancing act. We usually aim for high accuracy in machine learning, but this research shows that the more accurate a model gets, the more vulnerable it becomes to these MI attacks. It's a real problem, especially in fields where accuracy is super important, like medicine or finance. We need to find new ways to get that high accuracy without putting the privacy of the training data at risk.
Right. It can't just be one or the other.
Exactly. One promising way to do this is to develop tougher defense mechanisms. Things like differential privacy, adversarial training, and messing with the model output, like we talked about. These can protect against MI attacks without hurting the model's performance too much. We also need to look into totally different machine learning methods that are built with privacy in mind right from the start, like federated learning. That's where you train models on data that's spread out across different places without actually sharing the raw data itself. That could be a way to keep things private while still getting good accuracy.
Yeah, that makes a lot of sense. This whole deep dive has been incredibly insightful. I mean, it's really shed some light on this complex world of model inversion attacks and defenses. Just to recap for everyone listening, and remember, you're all experts here. What are the main takeaways? What should we be keeping in mind?
Okay, so first of all, MI attacks are a real threat. They're not going away, and they're only getting more sophisticated as AI gets more powerful. This research shows that even models that seem harmless can be used to steal sensitive information. Secondly, we can't just focus on making models more accurate. We need to start thinking about privacy from the very beginning, building it into the design of our models. That means using those strong defense mechanisms like differential privacy, adversarial training, and output processing to protect against these attacks. Third, tools like MIBench are going to be essential for understanding these attacks and defenses better. They let researchers test and compare different techniques in a really systematic way, which helps us move forward in this area of AI security.
It's like having a common testing ground that everyone can use.
Exactly. And lastly, we need to keep researching and pushing the boundaries. We need to stay ahead of these threats. That means exploring new machine learning paradigms like federated learning that put privacy first. And it means looking for proactive defenses that can stop attacks before they even happen.
Well said. Thank you so much for joining us today and for sharing your expertise. This deep dive has been incredibly informative, and I think it's given us all a lot to think about. To all our listeners, thanks for tuning in. We hope this episode has given you a better understanding of the challenges and possibilities in dealing with model inversion attacks. Until next time, keep exploring, keep pushing the limits of machine learning, and most importantly, keep the conversation going.